Hash Table Programming with C. Introduction. This book is an introduction to the hash table data structures when implemented and used appropriately. Hash tables are exceptionally efficient data structure for representing sets and lookup tables. They provide constant time, low overhead, insertion, deletion, and lookup. This book assumes you are familiar with programming and the C programming language. The theoretical part of the book also assumes some familiarity with probability theory and algorithm theory, but nothing beyond what you would learn in an introductory course. Hash tables are constructed from two fundamental ideas: reducing application keys to a hash key, a number ranging from 0 to some n minus 1, and mapping that number into a smaller range from 0 to n minus 1, n minus 1, where small m is very smaller than a capital M. You can use the small range to index into an array with constant time as well. Both ideas are simple, but how they are implemented in practice affect the efficiency of the hash table. Consider figure, which illustrates the main components of storing values in a hash table. Potentially complex application values are mapped to hash keys, which are integer values in a range of size and usually 0 to n minus 1. In the figure n is equals to 64. Doing this simplifies the representation of the values. You now only have integers as key, and if n is small, you can store the integers in an array of size n. You use their hash keys as their index into the array. However, if n is large, this is not feasible. If, for example, the space of hash key is 32 bits integer, then n can be approximately about 4 billion, slightly more than 4 billion. An array of bytes of this size would take up more than 4 GB of the space. You should need between 4 and 8 times as much memory to store the pointers or integers, for example, which are still simple objects. It is impractical to use this size of an array to store some applications keys. Even if n is considerably smaller than a 4 byte boards, if you plan to store n that is small n, very smaller than the capital N, you waste a lot of space to have the array since the array needs to be allocated and initialized. Merely creating it will cost you big O of n. Even if you get constant time insertion and deletion into such an array, the cost of producing it can easily swam the time your algorithm will spend while using the array. If you want an efficient table, you should be able to initialize it and use it to insert or delete n keys, all in time big O of n. Therefore, n should be in big O of n. The typical solution is to keep n large, but include a second step that reduces the hash key range to a smaller bin range of size small m, with m belonging to which m belongs to big O of n. This example uses m is equals to 8. If you keep m small, that is in big O of n, you can allocate and initialize it in linear time and get any bin in constant time. To insert, check or delete an element in the table, you map the application value to its hash key and then map the hash key to a bin index. You can reduce two bin indices in two steps. The first step, mapping data from your application domain to a number, is program specific and cannot be a part of general hash table implementation. Moving from large integer intervals to smaller, however, can be implemented as part of the hash table if you resize the table to adopt it the number of keys you store, you need to change M. You do not want the application programmer to provide separate function for each M. You can think of the hash key space, where n can be from 0 to n minus 1, as the interface between the application and the data structure. The hash table itself can map from this space to indices in an array from where m can belong from 0 to m minus 1. The primary responsibility of the first step is to reduce potentially complicated application values into simpler hash keys. For example, to map application relevant information like position on a board game or connection in a network down to integer. These integers can then be handled by the hash table data structure. The second responsibility of the function is to make the hash keys uniformly distributed in the range and the beginning strategy for mapping hash keys to bins assume that the hash keys are uniformly distributed to distribute keys evenly into bins. If this is violated, the data structure does not guarantee expected constant time operations. Here you can add a third step between two previous that map from end to end and scramble the application hash keys to hash keys. The better distribution. See the figure 2. These functions can be application independent and part of hash table library. This is the second figure. Its application map values to keys but they are not uniformly distributed, then a hashing step between the application and the beginning can be added. In chapter 6 and 7, we will return to this function. Having a middle step does not eliminate the need for application as function. You still need to map complex data into integer. The middle set only elevates the need for an uneven distribution of keys. The map from application keys to hash keys still has some responsibility for this term. If it maps different data to the same hash keys, the middle step cannot do anything but map the same input to the same output. Strictly speaking, you do not need that distribution of hash keys to be uniform as long as the likelihood of two different values mapping to the same key is appropriable. The goal is to uniformly distribute hash keys which are easiest to work with when analyzed theoretically. Performance when analyzing theoretical performance. The runtime results in chapter 3 this assume this. And therefore you can as well. Chapter 7 considers techniques for achieving similar results without the assumption. Directly in the array, other index that has an binning function provide still. If m is relatively small compared to the number of data values, you are likely to have collisions, which occurs where two hash keys map to the same bin. All the different values are unlikely to hash to the same key in the range n. This does not mean that collisions are unlikely in the range m. If m is smaller than n and as the number of keys you insert in the table, small n approaches the small m. Collisions are guaranteed. Dealing with collisions is a crucial aspect of implementing hash tables. And a topic that covered is a sizable portion of this book. The book, the book is primarily about implementing the structure, hash table data structure, and only secondary about hash functions. When implementing hash table, the concerns are these. Given hash keys with application value attached to them, how do you represent the data so that you can update and query table in constant time? The fundamental idea is of course to reduce hash keys to bins and then use an array of bins containing values. In the purest form, you can store your data values.